Good morning, everyone. This is 11F today. This is a technique of integration. And essentially, this technique is the reverse of the chain rule. So the chain rule is for differentiation, and we're going forwards. That's one of our rules that we have, which enables us to differentiate certain functions. And so certain composite functions where there's a function inside the function. In this case, they're calling it g of x. And obviously, differentiation takes you forwards, integration takes you backwards. So if you can recognize that you have this form here, okay, which is essentially the same as this thing up here. Okay, you've got dy dx is equal to dy du. That's the same as this thing, f dash of u, if you like, g of x being u there. And du dx being here g dash of x. So that's just the chain rule written another way. If you can recognize this form here, then you can take it back to the original function, which is a function of a function, g of x being your u in that case. That's another way of writing it down. Okay, well, sometimes you won't recognize this, and in fact, there's a technique for this instead, and the technique is by substitution. So that's what we're going to look at today. So although sometimes you can recognize these things, there is a technique which often works. Doesn't always work, but it often works with the questions which you'll be given. Right, okay, so let's have a look at some of these questions. Sorry, just get this one. So let's have a look. Let's get straight into example 10, okay, so show the dynamics of this. So, okay, so let's find the indefinite integral of x square root of 3 minus x squared with respect to x. The dot dx at the end, they missed the dot dx, which we normally write. But yeah, that just means with respect to x. X is the variable which we're considering at the moment. The reason why they called it an indefinite integral, by the way, is because there are no limits on this. We have not got a limit of where it starts and where it ends to find out the area underneath a curve. So it's indefinite integration. We're just interested in the function which comes out of this. Or in other words, the function which we differentiate to get this thing here, okay, because it's the reverse of, or the inverse of differentiation. Okay, so you can see that we've got a product of functions here, but in particular, we've got a function inside a function. So we've got 3 minus x squared to the power of a half. So what we're going to do is say u is equal to this function inside a function. So we're going to say u is equal to 3 minus x squared. Now, in questions, you might have to identify that yourself, or sometimes there's two composite functions and you're not really sure which one to use, or there's a function of a function of a function. It can be quite tricky, this, but often questions will say what to use as substitution if it's a difficult substitution. Okay, so we've got u here is this thing here. So I'm just going to write down du dx as well. So that's pretty easy. Got minus 2x there. Okay, now this thing is not a fraction, but you can treat it like a fraction. So it's a thing. It's saying this is the derivative of x, but we can treat it like a fraction by splitting it up. Now there's no proof of that, but we're allowed to do it. So if we want, we can take this to the other side, and we can take this to this side, by timesing by dx and by dividing by minus 2x. Okay, and if you do that, you're going to get, I'm going to write it the other way round. I'm going to write dx is equal to du divided by minus 2x. So I'm going to do divided by, let's put the minus there as well, front, minus 2x. So all I've done there is times by the dx and divided by the minus 2x. Okay, right, now we can see that we've now essentially got this. We've got the integral of x square root of u dot dx. So now we've got two variables involved here. And u is obviously a variable which is dependent on x, but it is still a new variable which we've constructed. It varies as x varies. So this is a mess, frankly, because we've got two variables here and it says with respect to x. So we can't do anything here at the moment, but we can now replace dx with this thing here. So if we replace the dx, we've got x square root of u dot du over minus 2x. Now you can see if we treat that like a fraction, we can then say, well, if we could treat this dot like a times as well, then we can see that this x here cancels with this x here. And you can see that we're getting now square root of u divided by minus 2. Now, because that's a constant, I'm going to bring that constant outside the front as minus a half. Because we can do that with differentiation and integration. Any constants which are multiplying by our functions, we can take out and we can put in again. It's just going to make things a little easier. And I'm also going to write this in a form which is nice to integrate. So I'm going to put u to the power of a half there and dot du. So now everything is in terms of u. So we're differentiating with respect to u. U is the variable which we have. Obviously, if the x didn't cancel, we would have had an issue. Say, for example, this was x squared there, we couldn't have done this problem. So it's not that all functions integrate easily. It's just that the functions which you're being given to practice on do. It's a bit like factorization. Most quadratics don't factorize. It's just we start off with the practice with those ones which do factorize. Okay, once we've got this, let's just take this to the top left. So we're going to say let's raise the power by 1. So let's use the technique of integration. So we've got u to the power of 3 over 2 now, and divide by our new power. So divide by the new power is divide by 3 over 2. And now that's integrated, and I'm just going to put the minus a half back on the front. And we also, remember, have to add on the extra constant, which when you differentiate it going the other way would have disappeared. So we don't know if there was a constant in this function that you differentiate in order to get this function inside here. We have to put that plus c on. Okay, well, it depends on how you want to deal with this one. Dividing by 3 over 2 is the same as timesing by 2/3. So maybe let's take another step on this one. We've just got that plus c on the end. And you can see that the 2 is going to cancel. And you're left there with minus a third u to the power of 3 over 2 plus c. Now, we've got one final step to do because this question said nothing about u. U is something which we invented here. So we need to replace u again. So we need to call this minus a third. And the u was 3 minus x squared to the power of 3 over 2 plus c. And that's fine, of course, to leave it like that. Although, if you wanted to, you could put it in a different form. Say this is the square root of 3 minus x squared all cubed plus c. So that would be a similar thing. That would be the same thing, and both would be right. Okay, let's just check that we've got that right. Let's see that I haven't made any mistakes. Yeah, that's what they've got there as well. You can see this. You can work through this if you wish to. Right, let's have a look at example 11. So let's take this one here. So find the equation of the curve passing through the coordinate point 2, 1 with the derivative dy dx equals to e to the 2x minus 2. Okay, so we can see we've got a function inside a function here with our derivative. And in order to find y, we're going to need to undo the differentiation. Now, undoing differentiation is integration. So what we need to do here is to find y, we need to take the integral of e to the 2x minus 2. Now, the point 2,1 we can worry about in a bit. You'll notice that I've forgotten something here, and it's important that you don't forget this. I've forgotten my dot dx. And it's important because we're going to change that variable, and we're going to need to substitute in for the dx. So we need to keep that in. We need to always write that when we're doing differentiation. What is it with respect to? Okay, so again, here we're going to say, well, u is equal to 2x minus 2. The u dx is just equal to 2. And then dx, on the left-hand side here, is going to be du divided by 2. So we're going to substitute that in. So next step, we're going to say this is the integral of e to the u dot du over 2, and that's equal to y. Now, in this case, there's no 2 to cancel with in front here. So again, we can just take out that constant of a half. So that's my next step. I'm taking lots of steps here, of course. e to the u dot du. It's all with respect to u now. And now we can integrate this. Now, e to the x differentiates to e to the x, and the same with e to the u. So when we go backwards, we're still going to get e to the u. So we've got a half e to the u, and then we've got plus c there as well. And that's equal to y. Now, we've got this coordinate point 2, 1. But before we can use that says nothing about u, we need to change this u again. So u is equal to e to the 2x minus 2 plus c there. So there's our function. Let me just check that I've got that right, just in case I've made any mistakes. I want to redo the whole thing. Yep, there we go. We've got the same thing. Now, that's not finished, obviously, because we don't know what c is. So we need to find c, and that's where this extra point comes in. So now we can substitute this thing in. I would normally say to the examiner, put the 0.21 into this function. Let's just put in 1 equals half e to the 2 times 2 take away 2, so that's e to the 2. Okay, I'm missing steps a little bit here just to keep the page neat. And then plus c. And then, of course, you can see what c is. C is equal to the 1, take away a half e to the 2. Now, you can evaluate that if you want to. I think that's what they do in the book, or you could leave it like that. So our final function in this case is going to be y equals a half e to the 2x minus 2 plus 1 minus a half e squared. That's just replacing our plus c, and that's finished. You can evaluate this one, and if you do evaluate it, leave it to 3 significant figures. Okay, and that one should be done. Let's just have a little look back through again. Let's just see the next page. Yeah, you can see they've evaluated this thing here as well. They just put an approximately equals to. Okay, so just to recap, because there's a nice little box before the questions there. It says the reverse chain rule methods can be used whenever the integral contains the product of a composite function and a multiple of the derivative of the interior function. Right, so if you have a look at that, for example, the question which they came up with, let's have a look at this one here, you can see that what's on the outside is the derivative of what's on the inside. So that cancelled when we replaced our dx with du divided by that derivative. Cancelled with this thing on the front. And they say a multiple of the derivative because they mean it can be scaled up or down because that's just a constant that you can take in or out. Okay, in these cases, this function will cancel when the substitution is made. Now, I always suggest using a substitution, but sometimes, once you've had lots of practice, you'll be able to see some of these quite quickly. But either way, you should still show you're working out. Okay, and there's the technique again. The interior function is replaced by the variable u. Du dx is evaluated. Dx is replaced by du divided by the derivative. That's what we just went through. Any possible cancelling should be carried out. Remaining function is integrated, and then the expression for x needs to be substituted back in for u. Right then, guys, hopefully that's all you need today. And for you to get on with the exercises, you've got 11F there, and in 11F you've got all the way up to question 9 there. Beyond this is definite integrals, which is where we're going to start putting in our limits and showing our techniques there. So yeah, get as far as you possibly can with this work today. Thank you for listening.